I put this up because they never put my original abstract into the index. So this is just to give you an idea. We'll actually break this up into two parts. The first part we'll talk about popular linear position sensors, and the second part we'll talk about the 4 to 20 milliamp current loops, because it's been my observation that the young folks coming out of college today have the foggiest idea what 4 to 20 milliamp current loops are about. So we may be able to help somebody that way. Unfortunately, it looks like we're all dealing here with people that have been around a while. As have I. Anyway, all right, so first thing we're gonna do, assuming this thing, I don't know whether I have to. She said it works.
Yeah, I think it works.
Yeah, okay, there we are. Okay, the alphabet soup of acronyms and terminology. LVDT, LVIT, blah, blah, blah. A pot's a standard potentiometer. Everybody knows what that is. The LVDT, people get all kinds of different interpretations of what the acronym is. That's the actual meaning of the acronym. And I ought to know because I wrote a book on the damn things. LVIT, linear variable inductance transducer. Sort of similar to an LVDT, or actually a DC LVDT, but lower cost and more or less similar capabilities. MLDT, now that's been messed around with for a number of years. Basically, it's a fancy word, magnetostrictive linear displacement transducers. There are half a dozen manufacturers in this country and in Germany that make these things, a couple of them in Japan. Basically, they're high precision, long measuring range type devices that use a toroidal magnet to be able to assess the position of the magnet along an extended probe. So that's what we'll talk about that later. Full scale. Everybody know what full scale means? Probably. I mean, in measurements, it means what do you get out of it? The 0 point or the start point is what is your zero? Although it's not always zero, it's some minimum. Now the non-contacting, this comes up because you'll see, I'll give you a chart later, that it has non-contacting and other times it says contactless, okay? Non-contacting means you don't need any mechanical contact between the sensor and the position, the sensor and the position device that you're trying to measure. Contactless means there's no electrical contacts inside. So potentiometers here have contacts as a rule. There are some so-called solid state or Hall effect potentiometers, but they're pretty expensive and they're also terrible with temperature. So they're not very popular. Finally, this gets into an interesting point. An active transducer element. That means one that has self-contained energy. Good examples, piezoelectric devices. Also, devices that work using permanent magnets with a magnetic field, a Faraday law type output gives you an EMF. Passive transducers, that's basically everything else. Are you able to see all right, or am I in your visual way? Why don't you move into one of these other ones, and that'll make it easier. Anyway, go ahead.
So as an example, where would a PIR, passive infrared sensor?
Let me get into that. In the very next picture, oh, come on. Mechanical, I'm only talking about mechanical input devices, not optical, not laser, not temperature, not radiation, none of those. Those are all potential sensors, but they're not mechanical sensors. So they don't work in an electromechanical system. Obviously, some of them can be active. For example, certain kinds of optical devices are self-contained. You don't need to have any necessary external power. Now, in the case of piezoelectric devices, you get an output, but it may not be useful unless you have some kind of a charge amplifier, as it's called, or high impedance isolation amplifier, so you could look at it, because it's not capable of delivering any real current, okay? You know, you can get lots of voltage, by the way. You know, these little igniters you use for starting your charcoal fire or whatever. You know, that's one of the things that happens. But here, what we say is this: first off, what's a transducer? Anything that changes one form of energy into another. This is universally recognized as the attitude. What's an electromechanical sensor? That's what I'm talking about today. Device that responds to mechanical input and electrical output. Don't say what the electrical output is, blah, blah, blah. Mechanical inputs, pressure, force, position, velocity, acceleration, sound, okay? Ultrasonics, for example, okay? But I took away those things that are essentially, you might call radiation, like light or optical or temperature or whatever. All of those are what I would call things that are covered by the radiation rubric. Okay, now here's the thing about sensors. People don't always recognize this, but there are many different ways to think about a sensor. The thermostat in your house, if it's an ordinary one, not a Nest or something, switches on or off when the temperature changes an input, the threshold. So it's not, it's of course one of these guys, but the point is it's state change that you get as a result of the something happening with the measuring, the device being measured. By the way, I used to have it, but I cut down the wordage. The thing being measured, the item that you're trying to get information on, it's called the measurand in the, if you want to look up in ISA 37. So you can have a state change, you can have a proportional output, which in the analog case is a voltage or a current that tracks whatever the mechanical motion is that you're trying to measure. And then you can have what I call digital or quasi-digital. For example, you can have pulse counts or a PWM. A PWM is sort of a digital, but not quite. It's neither fish nor fowl, as they say. You can have bits. You can have a frequency output from some things, for example. And all those go under the digital or quasi-digital rubric that I'm using here. Another thing about what I'm talking about, linear position. I'm talking about linear here means straight line motion, as opposed to curvilinear or three-dimensional or rotational motion where you use a tactometer, for example. And then macro. Oh, sorry, I went down too far here. Let's go back. Macro means it's large scale, from fractions of an inch to several feet, whereas micro is like strain gauges, for example, or other things that sometimes laser measurements that are in the very, very small distance or dimensional case, okay? So here's a pot. I started out with pots. Pots are very simple devices. They're variable resistor typically with a slider that goes over here, moves up and down. So you start from the maximum voltage, you come down to the minimum voltage, and it represents a reasonable way to measure position. However, this slider has a mechanical connection, has a rod that sticks out. So you move back and forth on it. That allows you to measure the position. Now you got to calibrate this system somehow. You can't just say, okay, I can tell you that if it's a 10-inch range pot and you've got half output, it's at 5 inches. So you have some idea of that, but it's not necessarily the whole ball of wax. I'm not gonna spend a lot of time on the pots. I should say one thing about a pot. I'm sorry. One thing about a pot. A lot of people don't understand this, especially people that are unfamiliar. But the only thing that's important about a pot is that whatever the E out load is, it has to be some high resistance. Because if it's a low resistance, then you're going to have current that comes through this here and then goes through the load resistor here and not get the division, the equal division that you're talking about. Does everybody understand that point? A lot of younger people think, well, okay, it's a pot, I just hook up to it. Well, yeah, you hook up your voltmeter and you have iron piece load. Hook up your whatever else, and maybe it gives you completely wrong thing. And in fact, if the load impedance or resistance in this case, because it's DC output, if it's too low, you have a totally unlinear output. It won't be at half scale. It won't be a 50% of the input voltage. It could be 10%, or who the hell knows what it is. Just a point. Okay. So now we'll go down to LVDTs. Linear variable differential transformer. We notice the words secondary, and primary. Okay, here's the primary. So you have three windings here, and then you have a ferromagnetic core. Now, people have built their own LVDTs using a nail for the core, or a piece of rod, a steel rod. But the cores of the commercial LVDTs are actually high permeability materials, usually about 50% nickel and 50% iron, or something thereabouts. What happens is that these things get hooked up in a differential manner. Oh, here's the inside of one, just to see. You see the windings in the core. They get hooked up in the manner that I'm showing here. Notice that the hookup is what we would call series opposing for the secondaries. Series opposing, not series 80. So the result is, when you have the core right in the middle, again, you can see from, I don't know, I guess I lost the top here somehow. But in this core, in the middle, you have equal voltages in each of the secondaries. So the net result when they're series opposing is some kind of very low voltage, equal quasi or almost zero. Okay, anybody ever use an LVDT here? Okay, LVDTs have been around for about 75 years. They started shortly after World War II to be commercially available. Okay, in the 1940s. Now, the fact is, they have a lot of advantages. They're purely inductive. They don't necessarily have much to do with electronics directly. Indirectly, they do. So they're very reliable. They can work in typically terrible environments like high temperatures and things like that. And because of the way they work, there is a repeatable point, namely the null point, this zero voltage position. It gives you at least some reference where the hell the core is if you want to have a stake in the ground. Okay? So it's a very useful tool from that point of view. And you say, well, where the hell are they used? Well, they're used a lot in commercial activities, but these days, almost all the shorter range and middle range sensors of position on an airplane are LVDTs. Why? Because they have this long history of reliability. Effectively, when you saw my picture a minute ago, let's see if I can get back there. I don't know if I can get back there, but I'm going up. I keep going the wrong direction on this stupid thing. All right, here we go. Now, I want to make this point. It's the same kind of a graph where you have the null position. Notice there's not necessarily a zero output, okay? That's because when you get to the point where you're at null, there are quadrature voltages that can develop and make a little offset, okay? Now, when you look at it down below here, and you see this is the DC output, you can make the null position go through zero DC. This happens to be a minus and plus, minus 100 plus the 10 dividends or whatever. The reason is because these two, as I showed you earlier, come on. You see where it says it's in phase or out of phase? Oh, there I go again. This is on one side of null. And see where it says here E out or E out is equal to E1 minus E2. Notice they're vectors or phasors. So if one is larger, if the one on one side is larger, it's 180 degrees out of phase. If it's on the other side, it's in phase with the primary. Understand? Now, what you do is you make up electronics that can detect that phase difference. So you can get it. This is the AC output here, but the DC output is reflected in this lowest here. Am I driving you nuts?
I have no idea.
Okay.
Thank you.
All right. How about you guys? Am I coming across or do I need to go into more detail?
It's interesting
how does this relate to artificial intelligence?
How does what?
How does it relate to artificial intelligence?
Because, what did I say in the first C, first? Artificial intelligence in the real world needs to get real data in the real world from real sensors. Okay, now when I originally sent this in, I told it was the abstract is what I put up there. That artificial intelligence ultimately either uses databases where it grabs information from, keyboard inputs or vocal inputs, or sensor inputs.
Yeah.
Okay, and as time goes on, it'll be more recorded information in the form of databases and sensor inputs, and less from operators or whatever. If you think about it, you know what the letters HMI mean? Human machine interface. Okay, as HMI spread more and more, it'll be, you got a few things you can put in the keyboard. The rest of the stuff either comes from hardware like sensors, or firmware and hardware and sensors, or from the database. And sometimes, it's not too common right now, but sometimes it'll actually be information that goes from the sensor into a database, and the artificial intelligence actually grabs it in almost real time from the database. You understand where I'm coming from on that? Because sometimes for control activities, you may want to know what happened just before the point of information and what happens after the point of information. For example, you're trying to control some kind of process. Well, you want to know, okay, you got some information. How quickly can I find out if the process was changed the way it was supposed to change? I may only know that by looking at historical after a minute or two, or I may know it immediately by looking at the output of the system real time. Follow me?
Yeah.
So, all right, so this is an LVDT. I'm spending a bit of time on LVDTs because they're very commonly used in a lot of industrial applications and, as I mentioned, in military aerospace applications. The thing about it is, when you look at my picture here, if I can go back to it, this is the wrong way again. Come on. If you can see here, there's only 6 wires that connect this up. And if you do it right, you can use only 4 wires or even only 3 wires. So you have three wire connections and a bunch of windings, and that's it. I mean, transformers are pretty straightforward. And by the way, how many times do you find a failed transformer in your life? Damn few. Okay? All right, so let's go back down here. Now, one of the things you can do, that when I showed you had 3 windings, 1 in the middle and 2 on the sides, the primary being in the middle and the 2 on each, 1 on either side of the secondaries. But there are other ways to make LVDTs. A lot of the aerospace LVDTs are like the top drawing here. This is called a tapered layer winding. By interleaving the windings this way, you can get the LVDT to be shorter for stroke. That factor, that parameter is called the stroke to length ratio. Okay. The simple bobbin LVDTs, like I showed you at the beginning, are relatively long compared to the stroke that they measure. But the aerospace type LVDTs, for example, are made in such a way that they can be relatively short. A bobbin type LVDT with 3 windings separated can only do at maximum, and that depends on a lot of the factors. Maximum, it'll be at least 50% longer than the stroke of the LVDT, maybe lots worse. But in the case of a taper winding, you can get up to 80 or 85% stroke to length ratio. So it doesn't have to be much longer than the length. Now, the other side of this is, sometimes you want a really long guy, and it becomes relatively expensive to make a taper layer winding. So for very long, they have what are called complementary taper winding. What you do is you break it up into segments. And if you notice here, this one is down here. By the time here, this secondary is large, and then this is large goes to smaller. And the primary is over here, and it's always the same. You understand? Now, it may look like this is narrower, but that's just because of a drawing fault. It's actually, they're all the same typically length in here, okay? So the primary is just spread out, and the two secondaries are made in this step fashion so that the overlap, like the one did up above here, okay? Now, here's an example of typical LVDTs, different sizes and shapes. Crappy picture, I admit, but here's, this particular one here actually is used on a Boeing 737. I forget what it's used for, but that's what it was made for. Here's a unit with a very large bore, and that's because you can put a pipe through the middle of it, and we'll see in a couple of minutes. As long as the pipe is non-magnetic, say stainless steel or some kind of Inconel or some other material that's not very magnetic, the AC field of the LVDT will get through the pipe to the core inside. So what happens in some cases, oops, is that the right one? No. I was going to talk about signal conditioners, but I thought I had another slide in here. Apparently, I'm not finding it. Well, anyway, this is the electronics you need to make an LVDT go. Okay. For years, people used carrier generator type systems. And then eventually things happen. Okay. Let me get to this one first. This is called the DC LVDT. It's a plain old LVDT, but with some additional electronics inside. With today's super small electronics, easy to do. All right. So what happens is you get a DC in, DC out device instead of AC in, AC out. It has all the features, but it has two limitations. Okay. One is the temperature limitation of the electronics, which at most 125 C. The second limitation turns out to be the fact that the DC outputs from DC LVDTs are relatively limited. You don't get a chance to make the output variable or, higher or lower. Historically, the original DC LVDTs going back to the 1970s were bipolar outputs, like the AC was, the bipolar. And then that's sort of gone by the wayside. For the last 20 plus years, everything is now unipolar. Typically 12 volts in or 24 volts in and 0 to 10 volts out, 0 to 5 volts out. Some of them have got 4.5 volts out to work with microprocessors and simple systems with A to D converters that are 0 to 5 volts, whatever. Okay. But anyway, I wanted to point that out. Let's see if here's what I was looking for. You see, here's some examples of LVDTs hooked up. For example, this one over here has a diaphragm, so you can measure low pressures with it. It's a common way of making low pressure sensors before the days of silicon-based units that are now capable of doing the same thing. Here's a guy where essentially this is a blanked off bore, and so it can be subjected to fluid, for example, as long as it's not a magnetic fluid, which is rare. But you can use this to put into various other mechanisms, like inside of a valve, for example. One of the places LVDTs are commonly used is in two-stage servo valves, where you have a pilot valve and you have a main spool. You want to know what the main spool position is to give feedback to the pilot. Again, you have to do an integration. The end result is you can use this. And here's an example of one where you have a float inside hooked up to the core, and it can measure liquid level as a point of interest, okay? So these are ways that the LVDTs were popularly used, have been used for years. Let's see, and I think I got through all the rest of these guys, so let's go over here. Now I'm going to talk about LVITs. As you saw in my early slide, linear variable inductance transducer, not a transformer, transducer. This is a cutaway, and basically what it amounts to is this. You've got you have a coil layer, single layer coil as a rule, okay? Oh, I should point out something before I forget. LVDTs are typically operated at frequencies on the primary between 1 kilohertz and 10 kilohertz, sometimes a little higher. But they don't work at 60 hertz. So if you buy one, don't think you can plug it into the wall or into a little transformer and make it work. It ain't gonna go. Not enough iron, okay? But they work from 1 to 10 kilohertz as the excitation. And the signal that comes out is, of course, some fraction of that. Most LVDTs are somewhere between 4 and 6 to 1 ratios between the primary and the secondary. So you can see that there are some differences. This guy has a coil, but the coil is excited at RF frequencies, 500 kilohertz up to maybe 7.5 megahertz, okay? So we'll talk about the electronics of that in a minute. Then what happens is there's another thing inside here. Oh, damn it, where I go again? Stupid thing. Oops. Oh, crap. I don't know why I keep pushing one button. I have a clicker that I didn't bring, and it's exactly the opposite of this, so I'm used to using the other one. Come on. This is why I said there's a chart, and you can see different kinds of position sensors and their relative value. We'll go into that shortly. Come on. Wonder if this thing ran out of battery.
That's what. Yes.
I don't know. All right. So the key point here is this piece here. As you see, this piece connects up to, hooks up to mounting arrangement. There's a rod eye in the back end of the body and a rod eye hooked to this rod, okay? Now, here's the important point. We call it a spoiler, some people call it target, doesn't matter what you call it. It's the moving member. All these things have moving members. So what happens is at these high frequencies, this material that I mentioned, damn, I have to warn I know the guy's coming up next, I have to warn him about this. Anyway, what happens is it's made out of conductive material. Now, it could be a conductive coating on a plastic part, say electroless nickel on a plastic part, or it could be something that's conductive like aluminum or copper, or even mild steel is a good thing, okay? We don't use the inductive effect of a ferromagnetic material. We use eddy currents. The surface of this becomes little eddy currents that it gets from the coil. If you're only into the coil a little bit, you have relatively small eddy currents. As you push it in more, you get more and more eddy currents. Those eddy currents establish counter fields to the existing RF field of that coil. So what does it do? Well, very simple. The eddy currents essentially reduce the frequency. Or, I'm sorry, if it's fully in, okay, you'll end up with higher frequencies. As you move it out, it reduces the frequency. So you'll be reducing the inductance. In some cases, reducing the inductance, what does that do? It's 1 over the square root of LC. So if you're 1 over L, if you get less inductance, the frequency goes up. If you get more inductance, the frequency goes down. So the output out of this device is essentially a frequency. Everybody clear on that? But frequency by itself is not easy to use. So let's see if this damn thing works now. So here's what we have in this device. We have a tank circuit, gets a frequency, it goes into a microprocessor. All this electronics is built in, by the way. It's a small, tiny module. The microprocessor has a clock. It stores information because, in this case, unlike an LVDT where it says linear, the linear applies to 2 things. One, as you saw in that V curve, you get a straight line on the output, so it's linear in that sense. But also, but the core also moves in a linear fashion, straight line, as opposed to curvilinear. Here, what happens is that frequency change, because it's a square root function, is not linear. So what you do is you put it into the processor, and then you have a calibration memory where you have a lookup table that straightens it out for your purposes. Also, you have a temperature sensor in it. Why a temperature sensor? Well, because this is a relatively low Q circuit. Because it's a single layer winding, not a lot of turns, a little few turns. It's higher frequency. Well, what happens is the Q will change with the DCR of the winding. So if you have the temperature go up, the resistance of the winding goes up, the Q's change, and that changes the frequency. So we put in a temperature sensor. This thing I'll tell about a minute. Anyway, when you get all done, you get some digital bits out of the microprocessor that goes into a D-to-A converter. And all this stuff down here is standard, ordinary analog circuitry. You have the ability to go into a buffer amplifier as a reference voltage, depending on where you want to set zero and other things. And then you have a current converter in case you want current output instead of voltage output, okay? So it's pretty straightforward electronic. It's nothing exotic. It's just that it's usually very tiny so you can get it inside of the house. Now, the thing that I showed you a second ago, these are available in sizes, just to give you an idea. This happens to be a fairly large one. This is about a 1-inch diameter housing, okay, with a 3/8 diameter moving member. But they come as low as 3/8 diameter and with, maybe a 5/32 diameter moving rod. And then they go up to, I think, 33 or so millimeter diameters. And they have a 5/8 diameter rod, as an example, just to give you some ideas. All right. Now, I'm going to try and go backwards again. Oh, going the wrong way, always. Oh, now I wanted to make a point about something. Here's the electronics for an LVDT. As you notice, it doesn't use a microprocessor normally. So you have a carrier generator, again, to make this audio frequency 1 to 10 kilohertz. You have an automatic amplitude control. Why? Because you want to keep the primary voltage constant. Everybody clear on that? Otherwise, it's going to change the output. And then you go into this kind of thing is no longer done very much, as I'll show you in a minute. But then you go into what's called a carrier amplifier and the demodulator. The thing about the demodulator is a phase sensitive demodulator. So we can tell 180 degrees here or 0 degrees there. And that's why you see this thing called a phase shifter. Okay. Oh, I'm not loud. I'm going to end up being that's the case by the time we get done here. All right, so the phase shifter is set up as the reference in the demodulator so that the demodulator knows this is based on something from the primary. All right, that's why it's going to automatic control. And then you have 0 adjustments and stuff for the amplifier, and out you go. Now, typically you can hook up isolation amplifiers, stages, or whatever, depends on what kind of output you want. These kind of things were useful when you had multi-channel devices, and they used those. These days, people are using what we call a DC amplifier type signal fixer. Basically, what they have is a carrier generator, the LVDT, a passive demodulator. That's one where polarity rather than phase determines what happens. And then you have a DC amplifier for the output. So this is similar in some ways to the function. However, as would be expected, eventually analog devices started making chips for this. They were not the first ones. There was a chip made by Philips, which was for an LVDT. Now, I'll tell you, let me see, what are we doing? Right? 12:58. Okay.
You're looking for time, right?
Yeah, I'm just trying to check out that I'm not running over. So, the original Philips chip, the guy that did it was one of these guys, that goes climbs mountains and works from midnight to 7 a.m. or something, And he didn't listen to anybody in the business about what to do. So when they produced their first chip, the NE5520, it was one of the world's best temperature sensors. So they went back to the drawing board and they got the 5521. And that was very widely used until they had an accident in their French facility and it burned down. And no more NE5521s. And that's when analog devices got into the act. So their first version was called the AD598. Now, these are relatively large packages compared. The NE5521 is a 14-pin dip. These things are 16-pin, and they're in a much larger package. So you see that you have here, I just want to point this out because this is the last stuff I want to have to say about LVDTs. They took the assumption, and again, not listening to anybody in the business, okay? And they took the assumption that the sum of the secondaries, even though you take the differential output to get the useful information, they took the added to the sum of the secondaries as a constant. So if you do a ratiometric input, i.e. this, you have what's called difference over sum. And that has an advantage, and I will talk about the advantage in a minute. If it worked, the problem is it didn't work because all the aerospace LVDTs are done in that manner, where the sum of the secondaries is constant. Because, and I'll tell you why in a minute, but many industrial LVDTs that you could buy commercially were not constant sum. And if you put it together in a ratiometric operation like this, you might have an LVDT whose specs are plus or minus 0.25% of full-scale linearity. Put it into this circuit, and now it's plus or minus 2% of full-scale linearity. You say, how the hell did that happen? That happened because the damn denominator over here, the damn denominator was changing because you moved the car, and it wasn't independent of core position. So they went back to the drawing board, and they produced this guy, which is the AD698. Now, the advantage of the AD698 is that they were taking, they thought they were doing something good. I had my own issues with AD, but anyway. So what they did is they decided they were going to take a different ratiometric arrangement. They were looking at the primary voltage and comparing it to the secondary voltages. Okay? And then I'll get into why this matters. And so they produced a chip that'll work with any LVDT, whether it's constant sum or not, because it's what we call absolute output. If you take an absolute output LVDT, all you really care about is what's that differential voltage and can I work with it? Well, here's the problem with an LVDT. Just like the LVIT, you have copper wire windings, especially for the primary. Okay? Everything in that LVDT is normally copper wire. Now, supposing you're providing a constant voltage, which is what most LVDTs are driven with, constant AC voltage, let's say 3 kilohertz, just to pick a number, okay? As that LVDT heats up, the impedance of the primary increases. Why? Because the DCR, the actual resistance of the copper, goes up the winding because of the temperature coefficient of copper, right? Everybody clear on that? The impedance goes up because the DCR goes up. The inductance doesn't change because the frequency hasn't changed. But it's the square root of x squared plus r squared. Everybody knows that, right? So the impedance goes up. Well, what happens when you have a constant voltage going into an impedance that increases? What happens to the current going through that? It goes down. Ohm's law for AC circuits. So what happens is the current goes down even though you're supplying a constant voltage. Whoa. Now what happens? Well, the LVDT works as a transformer. It transfers flux from the primary to the secondaries. If you reduce the flux, the secondary outputs go down. But it isn't because of the fact that the core moved that they went down, which is what you're trying to get. It happened because the temperature went up. How do you know whether the output change was due to the temperature or due to the core motion, right? Now, let me point this out. These guys decided to measure the primary voltage, okay? There are things they could have done that would have made sense, but they didn't. So they're still doing a ratiometric operation, but they're assuming that it's the electronic problem that the current went down in the primary. And it wasn't, it was the LVDT's problem. So they claim it'll work for any LVDT. My experience with people in the field is up to a reasonable limit of temperature, okay. But after you get past about 60 degrees C, you got problems. So these chips are available commercially. However, the NE5521, which was available from Philips, was a $2.50 chip. These chips are $15 each. So if somebody's going to use LVDTs or wants to experiment with LVDTs, and you buy the chips, just be aware that you got to put out some real bucks for these. And if you're designing it into something, be very careful. All right, now I'm going to go down here. This particular one actually had a hybrid on it, but we won't go into that. I mentioned all this stuff. All right, so we know about these guys here, and we know about how the electronics goes. As I said, you have the resonant circuit up there, which, by the way, is series resonant. Okay, but in spite of the fact that it's series, it's a Colpitts oscillator. I don't know if you guys know that stuff. I won't belabor it. Anyway, you got the microprocessor. That processor does the crystal clock provides a way of measuring the frequency. A binary divider, what's that used for, by the way, is to take the frequency and make it into a period, because the period is longer. And with the microprocessor, you can get more precision. That's why it says frequency and period measurement. And then the temperature measurement. The non-volatile memory is where you store the lookup table for the calibration. And then ASCII communication. Well, what is ASCII communication about? Well, what happens is, the thing about LVITs, many of them, you can do field programming to change the scale. So you don't necessarily, if you're putting it into a PLC, you probably say, well, what the hell, it doesn't matter much. I could make the adjustment to gain in the PLC. But if you're just using it in a simple apparatus, oh, I can adjust the output. And I have the availability of voltage outputs or a current loop output, okay? So I can use whichever one I want, depending on my application. And I can adjust it through ASCII commands. That's what the senset memory is about over here. You see, senset means sensor reset or sensor setting. So you have the ability to adjust it in the field. Now, for some people, this is very useful. And I'll tell you why. There are versions of LVITs made to go inside of a hydraulic cylinder, where the bore of the cylinder carries the moving member, and in the back end of the cylinder, even though it's sealed from the pressure, is the electronics. Now, maybe you only want to move the cylinder 9¼ inches, but you have a 10-inch cylinder, and you buy a 10-inch LVIT. I can now, very simply, by hooking up the right stuff, make it a 9¼ inch LVIT for full scale output, or whatever. You can adjust plus 20%, up to the 80 to 100% on one end of the scale, and 0 to 20% on the other end of the scale. So I can move the 0 around, I can move the full scale around. I have some very interesting features, okay? Now we're about 1:05, so I got about 15 more minutes. Let me go into the next topic, I think. Oh, let's go here. The magnetostrictive device. Like I said, there's a half a dozen companies that make these. What it amounts to is this. This is, believe it or not, this is actually what is called a time of flight, a TOF sensor, time of flight. Like ultrasonic or radar or LiDAR, it's time of flight. And what happens here is you have a piece of a magnetostrictive material. Magnetostrictive means it changes its dimension in the presence of a magnetic field. Clear? Magnetostrictive. Now, there are many different ways there are two different ways to do this. But right now, there's a current that's put through this wire from one end to the other. It's a current pulse. It repeats, boom, boom, boom. The current goes through the wire, which we call a waveguide. It's actually moving, it's an ultrasonic pulse, ultrasonic. And what you're depending on is what is the speed of sound in that wire, okay? When you know what that speed of sound is, you now have the ability to tell how far down the wire you got before you ran into this magnet, which gives a twitch to the wire. okay? That twitch sends back a mechanical pulse, which is what this thing here does. It looks at that mechanical pulse. And the electronics, what it does is measure the time from when you started the pulse to the time you get the twitch back. And since you have a constant sound speed, bingo, you can figure out where that magnet is. And there's literally, except for mechanical consideration, literally no limit on how long the wire could be. Okay, it's inside of the tube. That's what you see on the outside here, for to protect it against the environment, whatever it may be. So the magnetic field from the wire interacts, causes it to generate a strain pulse, the twitch that I mentioned, and that's what comes back. So that's how a magnetic-restricted device works. It's possible to do it a different way. It doesn't matter right now. If you ever get involved with one, you'll learn how they work. Okay. Now, this is a chart that I put together, and it essentially looks at a number of things. Potentiometers, AC LVDT. AC LVDT is a bare bones LVDT. DC LVDT has the electronics family. Half bridge I haven't talked to you about. LVIT I talked about, they need restricted. The ultrasonics, I'm just going to say this. I know a fair amount about ultrasonics. I was involved in that business for a number of years. The problem with ultrasonics in air, is that the speed of sound depends on the temperature, depends on the humidity, depends on altitude. Okay, so, and it depends on winds. And if you have winds that blow the sound away, you're kind of screwed. So I don't particularly give them a lot of hope. But this chart gives you some, not numerical, but rough idea of how good they are. For example, the ones that we're talking about for linearity, these magnet-restricted guys are capable of 0.1%, 0.05% linearity. That's the deviation from a straight line of the output. So they're very good. A lot of the other ones are get into good, very, very good as well. But anyway, so much for sensors, okay? Now, this is where I was gonna provide a timeout, but I'm running out of time, so and there's only a few people here, so I'll let you go. What I put in this was, if there was enough time, people could hit the head or whatever they had to do. So now let's go further. 4 to 20 milliamp current loops. This goes fast. Why do you use one in the first place? Okay, number one, the loop current doesn't vary with long field wiring. The resistance of the field wiring doesn't matter as long as you're below the compliance voltage of this loop. What's the compliance voltage? It's the sum of all the voltages that you use up compared to the loop supply. All right, so as long as you can sustain the current at 20 milliamps, you can make this as long as you want. Number two, because of the end of the loop, a current loop has low impedances, therefore not susceptible very much to noise and EMI. Now people say, well, yeah, but you're coming from a voltage source, you know, it's a high impedance. Yeah, but the loop itself has as a receiving element a low resistance, so it's not a big deal. Third thing about why do you use a current loop for networking? The large zero feature of the loop, namely the 4 milliamps, it's offset from zero, gives you a self-diagnostic feature. If there's something wrong with the loop, let's say the current goes to zero. Okay, you know the loop is open somewhere. A wire is broken, a connection, something's unplugged or whatever. Or you get a very low number, you say, oh, there's a bad connection someplace, okay? Now, here's another feature which is very popular in the real world. Current loop allows you to put other current operated devices in series with the loop. So not only do you have where it's going for the controls or whatever, you also take a field milliammeter and stick it in if you want to check what's going on and so on, okay? So there's a lot of advantages to that, especially for diagnostics, you know? If you're not sure where the problem is, this is a good way to get to it. And finally, if you're in a hazardous location, oil field or gas field or some other place, this maximum loop current, when you use simple safety barriers, is low enough current to prevent the ignition of flammable vapors. Okay, so you take a voltage device, let's say at 10 volts. If it's not current limited, it could have enough energy to spark the explosion. But the barriers allow you to limit energy involved in the current. Okay. Now, here's your typical current loop. And let's make a point of it. You got a loop supply. Usually it's 24 or 36 volts, but it could be anything you want within reason. It goes into a transmitter. Okay, you got a sensory input into the transmitter. That's what you're trying to measure. Now you have the wire here, the resistance of the wire going out, and the resistance of the wire coming back. It's all part of the loop. The 4 to 20 milliamp goes into the receiver. Typically, let's say it's a load resistor to PLC, right? PLC load resistor, 250 ohms, 500 ohms, 100 ohms, whatever. 250 ohms is the most common, and that gives you a 1 to 5 volt signal to work with going into your system. If you use a 500 ohm loop load resistor, you got 2 to 10 volts. Depends on what the A to D converter is that's on the front end of that device, okay? Now, I'm gonna make a point here. This is the loop load resistance for loop supply for a typical current loop. They pretty much look all very much like this. This says that your minimum compliance voltage is 15 volts. But if you put in 24, you have the ability to get about 800 and some ohms. You put in 32, which is obviously the maximum for this device. You can get to 1100 and some ohms. Okay, here's the point. With these kinds of abilities, you can have 2 or 3 devices into that loop without affecting the current at all. So, all right, now let's go to the nitty gritty. There's three general kinds of current transmitters. This device is called a transmitter by the people that use them. That happens to have stuck over the years with the industry, especially in the process industry. So they refer to a pressure transmitter or a flow transmitter or a temperature transmitter. They're all producing 4 to 20 milliamps, okay? Now, a 2-wire transmitter normally functions running from the energy already in the loop. It uses the current below the 4 milliamps, typically about 3.5 milliamps of current at some voltage, which is determined to some extent by what you have applied for. But the important thing is it's a sinking device. Everybody understands the difference between sourcing and sinking. Sinking means you're using up energy. Sourcing means you're putting out energy. Simple as that. Now, 3-wire transmitters are independently powered current loop devices, and they're sourcing. They're giving you out energy current. 4-wire transmitters are independently powered sourcing, but they're used when you need loop isolation. I'll show you that in a minute. The purpose of that is for noise around the, or for intrinsically safe operation with certain barriers in hazardous locations. The hazardous location is specified by the National Electrical Code, section 500 and 505. Then there are derivatives of these which act as loop isolators or current loop repeaters. These are often included in the safety barriers. Okay, all right, enough of that. Here we go. Oops, wrong guy. Oh, going in the wrong direction. All right, here's your 2-wire current loop again. As you see, there's only 2 wires that exist for the loop. Goes through here, comes around here, comes back here. Oh, I'm sorry. Oh, damn it. This clicker's gonna kill me yet. Of a heart attack again. Anyway, the one I had before here a minute ago. This is a 3-wire transmitter. What happens is you have power coming in, and then you have 2 wires that run out the loop. Okay. All right, here, let's go back. So, notice the 3 wires. You got this wire runs continuously through. We'll call it the ground wire or the return wire. You have 1 wire from the power supply, loop supply, and you have 1 wire that runs the loop, okay? Now, what's the difference between 2-wire and 3-wire? 2-wire are very popular with people that don't want to use a lot of wire or have long runs because the copper costs money. and it's gonna cost a lot more in days to come. 3 wires have the advantage that you still only need 2 wires going out to the, working with the device, going back to your loop. And you can put the power supply, for example, inside of an explosion-proof box or something else. But the 3-wire loop supply, the 3-wire transmitters are much cheaper than 2-wire transmitters as well. And to give you an idea, it's usually a 2-to-1 factor. You know, a 3-wire transmitter might be $300, and a loop power transmitter is $550 or $600. Okay? Now, 4-wire transmitter. Here we see that it's kind of a hybrid between the 3-wire and the 4-wire. As you can see, the power supply is completely isolated from the loop. The loop portion is still the 2 wires, but it's a 4-wire unit. So, why do we use a current loop? The fact is, it's the dominant analog system in much industrial application, especially processors or control applications, automotive plants, whatever. I realize there's some digital stuff that's out there that's taken over. It's also very simple in terms of connecting it up. You don't have a lot of work to do. So the item here is simplest, and it's also less wiring connected. The big point is it's superior as the current won't diminish, unlike the voltage up with this. Tell them to come in.
Yeah.
It's probably the next guy.
Yeah.
It's relatively insensitive, prevents a local readout. And one of the most important issues is it's self-diagnostic. That's very important because when you're working in the field, the last thing you want to do is to sit there and scratch your head. The self-diagnostic part of it is very useful. And so, what are the drawbacks? Well, 4 to 20 current loops, damn it. 4 to 20 million current loops only transmit data from one device. You don't have combined loops. I'm winding up in 30 seconds.
Oh, okay, someone said they needed help.
No, I don't need help. My problem is with this damn clicker. Multiple loops are required for applications where there are many sensors. A lot of field wiring is needed. This is the key problem with multiple loops. You can get ground loops and other kinds of deleterious things. And as a result, isolation becomes more complicated. Now, one simple way, by the way, to get isolation, and I haven't put it on here, or maybe I should have, is use a separate power supply for each loop, independent power. Lo and behold, as long as you don't have ground loops, you're in business. So it's something worth thinking about. And with that, I think I'm done. And I hope that you found something useful in all of my blabbering.